Thanks, Svenja, and thank you, Peter, for the great OPM sensor introduction. So as Svenja said, I will move from the sensors to the sensor array and try to explain to you what it buys us in comparison with the squid-based MEG system. I think it's a good thing to use the squid, the conventional MEG, as the sort of the baseline here, because most of you are familiar with that. So it probably makes more sense to talk about things in relationship to conventional MEG rather than give some kind of absolute numbers. As Peter already showed in his last slide, so the big thing about OPMs is that we can get them closer to the brain. So this is a realistic illustration of an adult in a conventional MEG system, and if we quantify the distance from the brain to the like each point in the cortex to the nearest sensor, so the average is something like 4.5 centimeters. And of course, if you're measuring a kid, so then this distance would be quite a bit larger, I mean, even larger. Now, if we can put the sensors on the scalp, or roughly on the scalp, as we can do with OPMs, and then they would track the shape of the head, so this distance would go to less than half. So in the same adult, that would be on average something like 2 centimeters to the brain. So this is, of course, all very nice, but let's look at the squids versus the surf OPMs again. This is a bit of repeating what Peter just said. So the big thing is the distance difference to the scalp and hence to the brain. Noise levels are different, as Peter also explained. I have, well, a bit narrower range for the OPMs. This is mostly the commercial options available for MEG. Bandwidth, there is also a difference. Squids intrinsically, they go to gigahertz range, so it's only the electronics that limits your bandwidth, not the sensor intrinsically. And then the field, max field, so Peter discussed that already. So squids are not even sensitive to the absolute field, they only measure changes in the field, and this of course has some implications to the shielding requirements, whereas OPMs, the surf OPMs, indeed measure the absolute field. And then there is a temperature difference, cryogenics, or some heating. But again, let's first focus on that reduced distance to the brain and what does that bring us. So to quantify that, we have conducted simulations, and I present the results from one of them. So for this simulation, we performed sort of hypothetical measurements with arrays of 100 magnetometers, both squid magnetometers and OPM magnetometers. And we took the geometry from MRIs of adults, so 10 subjects. So that should be pretty close to an actual measurement, so that the results should be valid in practical terms too. And now if we quantify the amount of signal, and now here what we took as the amount of signal was the norm of the signal vector. So you take the sort of root mean square sum of the of all the channels you have. And then what is shown here is the ratio between those signal vector norms for the squid system versus the OPM system. So bigger numbers than 1 mean that OPMs give you more signal. And now the color code shows you how big is this ratio, and you can see that in the frontal cortex you can have 3- or 4-fold larger signals from the OPMs. The reason why it's in the frontal parts is that because that's usually where people leave the gap in the squid helmet. So the squid-based system usually gives the smallest signal to cortical sources in that region. Now, if we focus on the sources in the central sulcus, so they're in the somatosensory cortex, so it's sort of orange-red color, so factor of 3. And now if we do an actual measurement in the same subject with a squid system and an OPM system, so here we used electric stimulation to the median nerve at wrist, So we get these responses from the first somatosensory cortex. And you can now see that indeed we get about factor of 3 larger signals with the OPMs shown below. Note that the scale bar is different for the SQUID and the OPM sensors. What is interesting is that it's not only the amplitude that is different. So you don't get the OPM responses by just scaling up the SQUID responses. And I think this is very interesting because it tells us that we actually get some different information with the OPM sensors that are closer to the brain. So the spatial aspect also brings us something new. And so let's focus on that one next. So from the same simulations, we quantified the spatial resolution. There are, of course, many ways to do that. One way is to estimate the so-called point spread function. So we assume, or we create the data, to simulate the data with point-like sources. And then we do the forward modeling to the sensor array. Then we do the inverse modeling as if it was a real measurement. And then using different inversion techniques, here we used the L2 minimum norm estimate, and then we quantify the extent of the result. So here we thresholded at 50% of the peak amplitude of the source estimate, and then computed the surface area that was kind of declared active based on this estimate. So the smaller that area is, the better, because the ideal solution would be just active in the cortex. So you can see that with OPMs, you have less spread, so smaller point spread functions, and thus better spatial resolution. Now, in order to understand that, how do we benefit from the OPM arrays in terms of spatial resolution? So let's look at one way to quantify how much spatial information there is, and also how many sensors we need to actually capture that. So in the previous simulation, we had 100 sensors, 100 SQUIDs, and 100 OPM sensors. So now what you see there is a sort of the general approach to quantify the amount of spatial information. So what is shown here is some examples of the basis vectors in a spatial frequency basis set. So this is now the description or decomposition of spatial information on an arbitrary surface, so in 2D. So this is analogous to having a time domain signal, and then you do a Fourier transform, so 1D Fourier transform, and then your basis functions are just the sinusoids. Then you get the normal spectrum. So it's the same thing, but this is now for spatial information on a 2D surface. And now the numbers, the 2, 15, 57, and so forth, so they are just like randomly picked component indices. So it doesn't refer to anything. They're just numbers. But they represent different wave numbers or wavelengths on that surface. So of course, the shorter the wavelength, the more dense spatially is the information. Okay, so this is just the way of quantifying things. So now let's look at the signal from a dipolar source as measured by an OPM array and measured by a SQUID array. So you see these two field maps there. What is characteristic is that the field pattern as measured by OPMs is tighter. So you have the maxima of the field closer to one another, and the extent is smaller in general. And that's, of course, because the sensors are closer. So the measurement surface, if you will, is closer. Now, if we try to decompose this field with the spatial frequency basis, so we can start with just take the first 10 components of this kind of an expansion. And you can see that you don't really capture anything of that dipolar source by just having the 10 lowest order components. They explain just 36% of the OPM measurement variance and close to 60% of the SQUID measurement. Then if we go up to 40 components, then we start to see something, actually in the squid measurement, you already can resolve the dipolar field pattern. It's pretty weak in the OPM measurement. Then if we go to 100 components, so the squid measurement already looks pretty much like having the full information that you can possibly get. The OPM measurement looks pretty good and explains 90% about of the measurement. Then if we go to 300 component, the squid measurement doesn't really change anymore, but the OPM measurement does get crisper. So there is still information to be gained if you go from 100 components to 300 components. Now, the number of components is not exactly the same thing as the number of sensors, but of course they are connected. So then if you want to make things simple, so then you could think of this being something like the number of sensors. And now the number of sensors is like with 10 components. Of course, you could measure this dipolar field with 10 sensors if you knew where to place the sensors. But now this would assume that you have sort of equally distributed the sensors around the helmet or around the head. And if you do that, so then you probably wouldn't catch this dipolar source pattern. And that's, I think, an important thing to notice, that if you have, say, less than 40 or less than 30 OPM sensors, and then you are interested in a particular response, you need to know fairly well where to place those sensors, or it might have source, because then you don't get anything of the field pattern in your measurement. This is not such a big problem with squid systems, even if you had that few channels. But of course, I think everyone who is using a squid MEG has a whole head system nowadays. So then in practice, this is not an issue with squid systems. Okay, but let's go back to that 100-channel simulation and again look at the ratio of the spatial resolution between the squid system and an OPM system. So that's plotted here in the color scale. So we typically get something like factor of 4 or so for the superficial cortical sources. And now, if we just make some comparison to other techniques we can use to measure brain activity. So this customary electrocorticographic grid has electrodes every 10 millimeters. And now if we take the spatial resolution that is, or separability of cortical sources that is thought of to be at the limit of conventional squid-based MEG, that's maybe on the order of 30 millimeters. So if you divide that by the improvement, so then we should get to similar scales as what you can resolve with ECOG. So that would actually be big news, because then you could apply an OPM system and do something non-invasively, which you would up to this point only be doing in an invasive manner, of course, only in patients. And why is this interesting? Now, if we look at ECOG data, so we get quite a bit more this high frequency activity, the gamma band activity, meaning stuff above 30 Hertz, compared to scalp EEG or conventional MEG. Of course, we do get those kind of signals in these modalities too, but not at the same with the same prominence as in intracranial recordings. So why would that be useful or interesting neuroscientifically? There are many reasons, but one nice thing is that it would bridge well to hemodynamic or vascular signals that we could measure with fMRI. So this blood oxygenation level dependent contrast is best correlated or shows the largest mutual information with the gamma band amplitude envelope of intracranial recordings. So now if we could do these kind of recordings non-invasively, so that could give us something that would go well with the hemodynamic measurements. Then let's move to the next point on the list, and that's the noise level. So as Peter mentioned, the squids are somewhat more sensitive than those OPMs that are now routinely used to do MEG. There is maybe a factor of